Coming up on Triangulation, I talked to Stephen Wolfram about his book, Adventures of a Computational Explorer. Well, actually, I use it as an excuse to go deep into Wolfram Alpha, the Wolfram language, and everything to do with the Wolfram engine and computational language. And in fact, we spend a little bit of time with Pokemon. There's a lot to it. You gotta stick around and check this out.
Podcasts you love.
From people you trust.
This is Twit.
This is Triangulation, episode 425, for Friday, December 13th, 2019. Stephen Wolfram. Triangulation is brought to you by Capterra. Find the right tools to make an informed software decision for your business. Visit Capterra's free website at capterra.com/triangulation. And by LastPass, a personal password manager and identity solution for businesses all in one. You only need one master password, and LastPass remembers the rest. Visit lastpass.com/twit to learn more.
Welcome back to Triangulation, where every week Twit hosts, in this case me, talk to the smartest people in the world about the most important topics in technology. Today, I am very excited to invite to the show Stephen Wolfram, the author of Adventures of a Computational Explorer. At least this time around, you're the author of this book. You've done quite a bit, including, of course, creating Mathematica, creating one of my favorite sites on the internet, Wolfram Alpha, and the Wolfram Language, as well as the author of A New Kind of Science. We thank you for joining us today.
Pleased to be here.
Yeah, it's exciting. So whenever I heard I was going to be doing this interview, I was like, oh, you mean the Wolfram Alpha guy? I was immediately pumped to be able to talk to you about that. But I thought we would actually kind of start at the beginning, as it were, sort of kick it back a little bit before that, because Mathematica came first, correct?
That is true.
Yes.
By 20 years.
By 20 years. All right. So tell us a little bit about Mathematica, sort of the creation of this technical computing system, and what was sort of the, why did you...
Why did I do it?
Yeah. Why'd you do it?
Right. Well, I mean, it kind of started when I was a kid. I was interested in science, and particularly in physics. And I kind of discovered that, to do physics, you have to do mathematical calculations and so on. I always thought the mathematical calculations were kind of boring. I thought these are very mechanical, automatable. Surely we can get like computers to do these for us. Well, that was sometime in the early 1970s when it was kind of hard to get computers to do much at all. But I learned how to use computers, and eventually I became sort of the largest user of the various kinds of experimental systems people have built to do mathematical computation. And then in 1979, I kind of realized I'd outgrown all existing systems, and the only way forward was to build a system for myself. So I built my first computer language computer system was a thing called SMP. It was a system aimed at mathematical computation, and that turned into a product and a company and all those kinds of things. And then I went back to doing basic science. And then by the mid-1980s, I had gotten to the point where I realized I need to be able to do more with computers, and I need to build sort of a framework for making computers to do the best they can, and hopefully something that would serve me kind of as my computational tool for the rest of my life. That was the theory. Mm-hmm. So I started building what became Mathematica, and that came out in June of 1988. And kind of my idea was automate the kinds of things that one needs to do in technical computing, mathematical kinds of things, and so on. But I kind of wanted to go back and understand sort of foundationally what is the ultimate set of things that one can expect computation to do. And that caused me to sort of build this computational language that is sort of based on very foundational ideas about symbolic programming and comes out of mathematical logic kinds of things. And that foundation of the language of Mathematica has become the thing that we've built on for the last 30-something years. It's actually very satisfying. I can take a Mathematica version 1 running on a Mac SE30 or something from back in 1988, and I can take a Mathematica notebook that I create in that and with code that's written in Wolfram language, take it, run it on a modern computer, if I can, convert the floppy disks and so on, and take that version 1 notebook, and it still runs today. So that's a very it's a reflection of the fact that we were dealing with very foundational kinds of things in the language that we built. But so Mathematica has been used for now 31 years by lots of kinds of people. It's really neat. I just last night I was at some fancy dinner, and I'm sitting next to CEO of a large company who told me, "Oh yeah, your product was really important in the work that he did in his PhD thesis." Usually you sell a software product, you don't actually get to know that much about what people do with it. But it's been very satisfying over the years that Mathematica has been used in all sorts of inventions and discoveries in lots of kinds of areas. It's basically every major university in the US, for example, has a site license for it, so it's widely used in education and so on as well. It's very satisfying to see that sort of a motivation to build from that foundation to other things, and that's kind of what I've been doing for the last couple of decades. And that sort of foundation of symbolic language, that sort of computational language idea, one of the big things that came out of that is the development of Wolfram Alpha, which sort of adds kind of the natural language understanding component and adds kind of this huge knowledge base of data about the world. And kind of the whole thing now we view as being based on this thing we call Wolfram language. And kind of the idea of that is it's sort of the world's the world's only full-scale computational language. It's a language that is intended as a way to express sort of everything in the world computationally, whether that thing might be, I don't know, the property of some food, or something about some movie, or something about a planet and where a planet is. It's something where the idea is that the computational language already knows a lot about the world, so it's easy to talk to it about things that one cares about, so to speak. And that's been a big thing for us in the last few years, is taking that computational language and making it as readily deployable in consumer and business, enterprise, and so on applications as possible. It's kind of the goal is to have it be the case that you walk up to a computer and you can take for granted the idea that the computer will not only have an operating system, a user interface, things like that, but will also have knowledge about the world. We'll have kind of computational intelligence about how to compute things, and it will know a lot of stuff that about the world to be able to do those computations with. So that's kind of that's been the sort of main thrust of a lot of things I've been interested in. I view it as being kind of the communication link between sort of the power of computation and AI and the stuff that we humans want to think about and want to do, so to speak. I mean, it's kind of we humans, we have sort of ways to formulate our thoughts, and computational language, the things we built, are sort of an effort to provide a framework for organizing one's thoughts so that they are able to be sort of put in computational form.
Okay. So the idea here is, instead of me as a human being having to approach the computer on its terms, approach these databases on their terms, and figure out how exactly do I communicate the thing that's in my head to get the computer to do the thing that I want it to do, or to tell me the thing that I want it to do. The idea is that I can think of things the way that I think of them, and the computer will tell me that information. So instead of me having to sort of completely restructure, I think of voice assistants that we have right now, where the idea is that I could say, "Hey, pal, can you set an appointment for my dinner later this week?" And unfortunately, you can't just do it like that. You have to sort of take it step by step and fill out all of this information. With Wolfram Alpha and with the computational language, is the goal here to make it so that we can communicate through our human means with the computers and get what we want out of them?
Yeah, I mean, there's different levels of this. So there's the there's programming languages which are really catering sort of to computers on their terms. Programming languages tend to have sort of the core of the language is just this thing that kind of tells the computer at the lowest level what to do. There's a lot of stuff built up around that kind of handles the bureaucracy of large programs and so on. But in the end, you're really talking to a computer on its terms. You wouldn't expect the programming language to know about things like, geography and all sorts of other things. You would, that's something that you have to kind of pull in, add in from somewhere else and so on. So that's, at one level, there's the programming languages, which are kind of catering to computers sort of down at the level of what computers intrinsically do. Then there are things like intelligent assistants. We actually provide the computational knowledge for Siri and Alexa. So there, what one's doing is kind of almost sort of drive-by computation. You say a short thing, and we've managed to be very successful in getting natural language understanding to work for the kinds of things that humans can say shortly, so to speak. The way that works is we're turning that natural language into our computational language, into our precise computational language. So let's say we say, what's the, how far is it from San Francisco to Los Angeles? Mm-hmm. That would turn into, geodistance of the entity, city, San Francisco, entity, city, Los Angeles. And then that will it'll then compute the answer to that, and then it'll kind of humanify the result and speak it back to us, for instance. But I think what we're trying to do with computational language is something sort of intermediate between those two levels. It's providing a framework for humans to formulate their thoughts computationally. Historically, you go back 400 years, when people were talking about math, they would talk about math in natural language. They would use words to say, add this to that, et cetera, et cetera, et cetera. Mm-hmm. And then mathematical notation, things like plus signs, equal signs, things like that got invented. And rather quickly, ideas like algebra took off, and then calculus and so on. And we got all the sort of modern mathematical sciences that emerged from kind of that fact that with mathematical notation, you had a streamlined way to represent and talk about mathematical concepts. What we're trying to do with computational language is to do the same kind of thing, but for the much broader set of things that you can talk about computationally. So it's something where it's a framework for organizing one's thoughts computationally in a way that's natural for people to do. That's the job of me, for example, as a language designer, is make something which is kind of ergonomic for the humans who are using the system, something which is natural for them to think in terms of. Mm-hmm. It's something where there's a small number of principles that people can learn and relate to, and then the rest of it is sort of follows from that. So it's kind of the question is sort of when do we reach the point where there's computational language literacy in the world? We've got it's like 500 years ago now. We got kind of written language literacy pretty broadly. There's a huge effort to get some level of mathematical language literacy in the education system. I'm not sure all of that is completely properly guided, but that's a different issue. But the thing that gets really interesting is when we have computational language literacy, when we can express ourselves in sort of a computational language, and that allows us to explain to AIs, computers, whatever, that explains in a precise way kind of what we want to have happen. So, in your example of making appointments and so on, well, there might be a little bit more detail to that. It might be, set your appointment, but avoid this and avoid that. You've got to be able to represent those things. Let's say, make sure that I'm going to go to this place, more than 2 hours before sunset, or, and make sure, and don't have me meet somebody outside if the air temperature is less than such and such. Well, if you can express those ideas, which you can easily in our computational language, then you can essentially define what amounts to, well, it's a kind of statement in computational language, or something you might think of as kind of a computational contract that says, this is what I want. Okay, computer, now go figure out what you figure out about how to make that happen.
Excellent. I was about to ask you for an example, and that was the perfect example there, to sort of understand what you mean when you say letting us or having that computational language literacy. That certainly makes sense. And so it's all of the little bits and pieces that come together to, as you said, it's like a contract that you're writing to give the computer exactly what it needs to know to give you what you want. So in the same way that the thing that I'm curious about here, there seems to be a separation, because with language literacy, the point there was for human beings to talk to other human beings in a streamlined way. With mathematical literacy, again, a lot of that is like human to human, where I can write down 8 and then this little horizontal line and vertical line and 2, and then 2 horizontal lines, and then 1 and a 0, and humans know what that means. But with computational language, that's specifically for talking to computers. So does that make it more difficult, or how does that work?
That's the neat thing. It's both for talking to computers and for talking to humans.
Okay.
And that's kind of a big difference between sort of the programming language idea and the computational language idea. Part of what is really important, I think, about our Wolfram language, the computational language we built, is that it's something that's readable not only by computers. I mean, the real superpower comes from having it be readable by computers and executable by computers. But there's another piece, which is having it be readable by humans. So just like if you're a technical person, you would read some technical paper, it'll have mathematical equations in it and so on. It might have a big blob of code, but that's probably pretty unreadable. The thing is, with our computational language, it's something which is kind of high enough level and kind of aimed to be something that can really express ideas as crisply as possible in computational terms. And so you have the computational language right there in the document. We have these things called notebooks that we invented actually back in 1988. They've become quite popular in recent years, but they're the same as they were back in 1988, although we've had 30 years to kind of polish how they work. It's kind of a notebook is a mixture of human language and computational language, and kind of the form of exposition that I'm really keen on these days is what I call a computational essay, where you're trying to explain something and you're using human language, but you're also using computational language as part of explaining your point. So the computational language is something that other humans can read, but by the way, also the computational language within the notebook is something that gets understood by a computer, and then the computer might produce an output. So like, for example, you might say, I don't know, make a, you have a plot of the tides as a function of time in your local. I think maybe you're near the coast. I'm not sure if you're near the coast.
Yeah, pretty near. Yeah.
Okay, so let's say that make a date list plot of the tide data for your place over this range of time, from now minus 3 weeks to now or something, and that's something where you can see that piece of computational language. And it's very easy to understand what it is, and it's very precise. Even though it's easy for us to understand, every piece of it is something that has a precise definition, and you can probably guess what it is, but right. You could go look it up and see that that's really what the definition actually is. But then the computer would generate the output and have it right there in your computational essay. So in a sense, it's a little more difficult to write a computational essay in the sense that you have to not just write sort of natural language, English text or whatever that other humans could understand, but you also have to write computational language that humans could understand, but also that is sort of precisely correct in the sense that you really are saying what you mean so that a computer can understand it. But then the big sort of superpower is that computational language then gets executed by the computer, and there you have this great result right there in your computational essay. And 3/4 of the page you create is done automatically for you, so to speak, and makes beautiful graphics or whatever else it is. So, but I think this idea of a computational essay as a way to communicate ideas it's a really powerful thing. And I think as we see these different fields of sort of human endeavor, I mean, for sort of almost anything called X, whether it's, I don't know, archaeology, zoology, literary criticism, television production, I don't know. There's sort of a computational X that either exists now or that will exist in the future. And the question is sort of what's the sort of language that allows you to express what you need to talk about for that computational X? And I think that's what we now have with our computational language. And I think what we'll see is the same kind of sort of explosion of possibilities that happened a few hundred years ago now when mathematical notation came in and when it was possible to start having sort of mathematically informed areas of science and engineering and so on. So it's kind of an exciting thing because it's this moment when we get this new form of communication that allows us to kind of take advantage of all that power that exists in computers and AI and so on. And this is kind of the bridge between our ways of thinking and what the machines can powerfully do for us.
Excellent. And so this is computational language in general, or is this specifically the Wolfram language? When you talk about this bridge,
Right.
Is it everything, or are you saying that this is what your organization is doing or is trying to do?
Well, we're it. I mean, this idea of making a full-scale computational language, a computational language that can express, that incorporates knowledge about the world, incorporates all these different kinds of algorithms and different domains of dealing with images and sound and networks and deploying interfaces and all these kinds of things. That idea of having this be sort of an integrated, unified system, we're the only ones who've been crazy enough to try and do something like that. I kind of started this. Our first sort of the foundations of the language were laid, well, actually, even in the very first language I built back in 1979 and so on. I tried out many kinds of ideas that have ended up in Wolfram Language, but Wolfram Language itself has started building in 1986. And sort of our first big use case as Mathematica and kind of mathematical and technical computation. But the thing that's been really neat is that those kind of foundations, those sort of computational language foundations, we've been able to just keep building and building and building on them into all of these different kinds of areas. And it's been strong enough to maintain sort of a coherence to the whole system. And that's been it's been really, really interesting to see because it's kind of like, I'm not sure whether we'll ever be able to do this kind of thing with computational language. And then we finally understand, like, I don't know, for example, a recent thing has been in the world of blockchain, let's say. We have nice symbolic representation of blockchains and so on. But more important, the kind of the hoped for killer app of blockchain, that is computational contracts, the ability to take what would normally be sort of a thing stated in legalese and turn it into code that can be autonomously executed. We have kind of our language is kind of the sort of the best game in town for a hope to be able to do that about sort of real kinds of contracts in the world. And that's been sort of it's interesting to see how the ideas of computational language extend to things like autonomous execution of computational contracts through things like blockchain infrastructure. And it's been really, from the point of view of, I mean, I've spent some part of my life doing basic science. In a sense, these ideas there are sort of very deep ideas about computation that have both informed things I've done in basic science and inform what I've tried to do in building computational language. It's sort of a funny thing because there's sort of deep ideas and results about how computation in the wild can work. And then there's us and the way we humans think about things. And in a sense, what I've tried to do with building our computational language is make the bridge between those two types of things. And in terms of, what exists out there, I mean, you look at standard programming languages, they've gradually advanced over the years, but the idea has remained pretty much the same. It's a wrapper around the intrinsic operations that a computer does, whether it's, arrays of numbers or loops or whatever else. People then add libraries to do particular things, and you get some tower of libraries that may or may not be compatible with the other or whatever else. What we've tried to do, typically those languages have, a few tens of sort of primitive operations in them. What we've tried to do is to integrate everything into this kind of coherent symbolic language, so that one can express sort of anything one wants to express computationally, one can express in this language. And so the result is there are, 6,000 primitive things. It's sort of comparable to the number of nouns there might be in English, so to speak. It's the same kind of order of magnitude, because it's expressing this. It's trying to express ideas, trying to express concepts, just like natural language expresses concepts about the world. So our computational language expresses concepts about the world, and that's so. It's kind of funny, because as we've gone on through the years, I've kind of realized just how far away from what other people have been trying to do or have sort of have chosen to do. I mean, it's a big project. If somebody had told me at the beginning, it's going to, 30 years out, you're still going to be intensely working every day to build this thing. It might have been difficult to convince to start the project. But
right.
But that's kind of what's happened, and it's an interesting process. Language design is a very exacting intellectual activity, because it's all about, how do you take these kind of collection of ideas and how do you kind of condense them to the point where you can express them with sort of the minimal set of primitives in such a way that those things are ergonomic for humans, so that humans can understand what's going on. I've had some fun last year or two, because for many years I've done endless internal meetings at our company about sort of the design of our language, and I always thought they were pretty interesting. And they're sort of a mixture of deep intellectual, almost philosophical ideas together with very practical software engineering. And I started about a year and a half ago. I thought, these are kind of fun. Let's live stream them to the world, just as a kind of form of entertainment. So I've now done, I think I've done about 500 or 600 hours of these things now, and I just did one this morning, for example. And I think it's this process of language design. I mean, it's not one that people really think about or understand in general. And it's a fascinating intellectual activity. And in the end, I think it's something very important, because in a sense, the language you define sort of molds how people think about things. I mean, I know that when I invent some new construct in Wolfram language, and I start using it, I realize I can think about a bunch of things in a different way than I've thought about them before. There are sort of thoughts that were hard for me to form before I had this kind of anchor sort of name for that kind of lump of computation, so to speak.
Wow.
Once I have it, I can think in terms of it. But this idea of language design, it's I think an as yet somewhat unrecognized power, so to speak, because it really defines how people think about things. And I think my responsibility as a language designer is to sort of build the tallest tower I can to let us humans take the best advantage we can of sort of the power that computation and the knowledge that our civilization has accumulated can provide for us.
Now, I do want to ask, where can folks, if they want to tune into these live streams, how do they find these? Is it available just at your website, or where do you go to see these?
Yeah. I mean, it's on Twitch and Facebook Live and YouTube Live. And you should ask my channel name, but I don't know what it is. But it's probably Wolfram, give or take. I'm a maker, not a viewer of my live streams.
Right. We will have to look that. We will find it for folks listening right now, and we'll include it in the show notes so that you can check those out as well. It's interesting you talk about building this tower, and of course there's that biblical story about the tower that was built, and how everyone spoke the same language, and then after that they didn't all speak the same language, and the tower was knocked down. I'm curious, when you started out with this with this whole idea, were you building this from the beginning for yourself and then realized how helpful it could be for other people? Or was it kind of from the get-go you wanted to empower humanity? And I'm talking like way back before even Mathematica was out, when you were first sort of understanding that there was something here. Were you just doing it for yourself, or was it for everybody, really?
Well, I was user number one.
Right.
Okay.
Right.
I wanted to make sure that it could do what I needed it to do. But I also full well knew that to do a good job, and a job that would be sort of even a job that would be sufficient for me over the long term, I had to make it something that would be broadly applicable. And so, I was really the extent to which people have been able to use the tools I built is very satisfying. It's hard to know for sure how that's going to play out. I think in today's world, a lot of the more technical tools that in Wolfram Language, for example, the more technical applications have been widely explored, and it's been very satisfying to see all the things that have been done with it. I would say in the more kind of, I just want to build software side of it, I don't think it's been nearly as much explored as it could be. I think, people win hackathons with it all the time because they're able to do kind of magic things that people say, how could you possibly do that? And I know it's 2 lines of Wolfram language code, so I'm so impressed. But I think that in the world of kind of sort of general software engineering and so on, there certainly are plenty of companies, including very large ones, that make good use of Wolfram language. But I think it is not as generally used as it should be. And it's an interesting issue because, in a sense, it's a funny thing because when I see the very sort of high end, the most sophisticated, technology R&D, software, CEOs of software companies and so on, it's remarkable how often they are serious, often daily users of our technology. And it's like, okay, why don't all the other people in your company use this too? Mm-hmm. They say, well, it's kind of, they feel it's too sophisticated. Now, on the other hand, we're also being rather successful at providing this computational language for kids to, learn ideas of computation. It works really well. I have kind of a hobby of teaching middle school kids this stuff because when I claim this is good for kids, and I got to actually do some field work and know that I'm talking about it. And it works great, really great. I mean, it's and I think there's sort of it's a funny thing in the world because this is, really embracing computational language as something that you do software engineering with is something that it just takes a little bit of, it's an inexorable process. I mean, I've been lucky enough in my life to see a number of things that even I've invented, which went from nobody can understand what this is, to, it's all obvious and everybody uses it type thing. Mm-hmm. And this is something where sort of we're still in the intermediate stages of that when it comes to sort of the mainstream software engineering world. I think it's been, it's one of the issues there has been kind of, okay, take Wolfram language, it's encapsulated in this thing called Wolfram Engine. And, we've been making it so you can really integrate Wolfram Engine into the middle of some big software stack in a convenient way and so on. And that's been a gradual process of us doing a bunch of engineering to make that possible. But I think in terms of, did I intend this from the beginning for everybody? The answer is, yeah, I certainly had that in mind. I didn't know how broad the everybody might be. I think my understanding of what is possible computationally has dramatically broadened since the early 1980s. I kind of had sort of a notion of what might be possible, but I hadn't really internalized some of the directions that computation could really go. I mean, but I certainly knew directions we could go. I mean, I was pleased that recently we finally finished my 1991 to-do list of. Oh
my goodness!
So
what was the last thing on the 1991 to-do list?
That's a good question, actually. Probably something quite mathematical and technical, actually.
He's like, you wouldn't understand.
Okay, so there were things like there were things about printer drivers, which were on the to-do list in 1991. They're gone today. Nobody cares about. Nobody needs a lot of detailed software tangling with printer drivers because that's kind of taken for granted in the operating system. I think the thing that you ask kind of who's the target for the kinds of things we try to do. I think that as I was saying, I mean, it's kind of the goal is to make computational intelligence of the kind that we've built become taken for granted. Something where, today, no self-respecting computer would come without networking capabilities, for instance. It should be the case that no self-respecting computer will come without knowing about computation, knowing a lot of, having a lot of knowledge of the world and so on, of the kind that we've tried to build. In other words, having it so that sort of one starts to take for granted this kind of level of computational intelligence and then build whatever one builds, do whatever one does from that base. That's kind of my goal. Mm-hmm. Making that happen is, I've spent the last, 40 years or so sort of trying to build that computational intelligence up. There's a sort of the process of making it something everybody can take for granted is a process that involves, lots of things in the world at large. But when I started, for example, when I started building Mathematica, it was a non-trivial thing to get a system as powerful as the one that I envisaged to actually run on computers that existed. Like, it was just straining the edge of what a Mac could do in those days. Right. PCs just couldn't do it. They didn't have enough memory. Today, actually the software engineering practices that we developed at that time that kept our sort of code nice and compact and so on, they're kind of cool for embedded processors today. But, we have a much smaller memory footprint than your average, web browser or something today. Those kinds of issues went away. But an important thing for me in terms of the sort of design process was that I, from the beginning, said this is sort of theoretically how I want this to work. Computers aren't quite here yet to make this really easy to deploy across a broad range of platforms, but we're going to build it the way we want to build it, and the computers will come, which they did.
If we build it, they'll come.
Right. And in terms of what we've done now with computational language, the goal is to be able to express all these things computationally, and to allow more and more people to understand just what is possible to do when you can express things, sort of routinely express your thoughts in computational terms.
We'll get back to Triangulation with Mikah and Stephen Wolfram. What a great guest. Fascinating stuff in just a second, but I want to tell you about our sponsor today, and it's very holiday-esque here, isn't it? Our show today brought to you by Capterra. It has been a great year for us and for Capterra. This was the year Capterra broke 1 million reviews on their site. Capterra is a directory of business software, all the best programs for any line of business. Yoga studio, dog groomer, whatever business you're in, dentist, medical office. It also has, of course, there's 700 categories. It has, the big name things like CRM and digital workplace software, things like video management software, really anything you might want to use in business. Capterra is a directory of. You can go to capterra.com/triangulation right now and use it for free. It's absolutely free. If you're suffering with old software, this is the time to start the year right with brand new, fresh software, state-of-the-art in every possible category. And one of the reasons I love Capterra, besides the fact that everything's there, it's very easy to search for what you want. Even use the check boxes to filter down. I only want 4-star and up reviews. I only want stuff that'll let me book appointments, or I only want, and each of those filters is really dedicated to that category of software. So, it really matches up what you're looking for. You can narrow it down. You can even do a side-by-side comparison chart of the software that you're interested in. Look at all the features on premises, in the cloud, things like that. And then that's when the reviews are so handy. More than 1 million reviews and just growing like crazy. And these are not just any old reviews. They're vetted. Capterra is very careful about making sure these are verified purchasers of the software or users of the software. These are people whose reviews really will be meaningful for you. And that saves you so much time because you don't have to try a product. You can just look at it and say, well, based on these reviews, this is the one for us. Capterra.com/triangulation. It's free. It's awesome. And with that many reviews, you'll find everything you need to make an informed decision. Be confident with your next business program. Join the millions of people who use Capterra every month to find the right tools for their business. Capterra believes that software makes the world a better place because software can help every organization be a better version of itself. Capterra.com/triangulation. It's free. CAPTERRA.com/triangulation. Capterra is software selection simplified. Now back to our conversation with Stephen Wolfram.
So I think one of the best ways to show the power of whatever it is that you happen to be working on, or to show why someone should check this out or try this, is to talk about the successes. And so I'm curious, what are some of the most your favorite things that have been created using the Wolfram language, using the computational language, and if not favorite, then maybe most surprising ways where because it sounded earlier you said, some people were going, wow, that was pretty incredible what was created, and you said, well, it was probably just like 2 lines of your language to make it happen. So maybe you're not usually surprised by what's being created, but maybe what are some of your favorite examples? And that could even go if it's something that a middle schooler did or was empowered to be able to do with your language.
Well, let's see. I have to remember, we do this high school camp for high schoolers every summer. Let me try and remember some projects from this year. I think one project, real simple thing, was ingest Twitter data and try and see, map the emojis of from different geotag tweets and put them on a map and say which country is the most does the most emojiing or something. I think it was another project actually from another kid. I think it was last year's camp. There was another Twitter one which was to use our built-in sentiment analyzer to compare tweets and their sentiment and compare that with kind of what emojis appear in the tweets and decide, which emojis are most likely to be associated with positive sentiment and so on. These are trivial things that, those are doable in I don't know how many lines of code that would be, maybe 4 or 5 lines, maybe less, in our language, and was done by high school kids in that case. I think those are a few small examples. I mean, I think what are some good examples?
That there is pretty incredible, because I think whenever I hear you say that, I'm sort of going, now what all would that take? And you've seen those, or at least I have seen those articles that come out that are showing that exact thing where, you have this country who uses this many of this emoji and what that means and how, and it's usually like a research study that's been done that involves so much work. Yeah. So the fact that you could do that in 4 or 5 lines of code is pretty doggone incredible.
Right. I mean, the fact is, this is routine, and this is why kind of the leading researchers in lots of areas use our stuff, and they're able to do amazing things with it. And I think that if you look at these different areas, whether it's digital humanities or something, here's a project. This was done by one of my kids actually. This is like 2 lines of code. It's like, where's the geographic center of the U.S.? So it turns out, people say, the center of the U.S. is somewhere in Kansas. Mm-hmm. Actually, that's based on something that was done in the early part of the 1900s. Somebody at the, I think, U.S. Geological Survey or something, cut out a map of the U.S. in cardboard and balanced it on a pin and found where it balanced. Okay? So we can do better today. But the question is, how much code is it to do that? And it depends on what map projection you're using, where the correct balance point is, and so on. But that's trivial now. And actually, as it happens, one of my kids did that. And, with most map projections, I think the center lands in Kansas, the summit, it goes as to Nebraska and so on. Again, a couple of lines of code to do that. I think I'll give you a different example. In sort of a much larger scale kind of thing. Well, if you look at like the quant hedge fund folk, a large fraction of those guys use our technology to study their strategies, sometimes implement their strategies. I don't know how much code they have. It's probably more secret than a bunch of the defense uses of our code. but that's a place where there's sort of large scale use of the system. Another example, a company I like quite a bit called Emerald Cloud Lab. Their goal is to automate biology and chemistry experiments of the kinds that things like pharmaceutical companies do all the time. And so they've taken, this sort of factory's worth of lab equipment, and they've automated it. And they use our language for everything. And kind of the way it works is you go to a website, you're using the cloud version of our stuff, and you give a script in Wolfram language that says, take the test tube, shake it this way, run it through this test, do this, do that, and then put the results back in the cloud to look at. Mm-hmm. And that it's kind of nice. They're always fun because they use our language down to the level of every machine in their kind of factory floor, so to speak, is labeled with a piece of Wolfram language code and so on. And that's a sort of big deployment of our language, which involves doing all kinds of things from planning stuff for robots to doing data science, data analysis, to doing things with chemistry and knowing about molecules and so on. It's a pretty broad use of the system that we have. I mean, I think I would say that if you look at kind of doing data science, our language is really widely used for data science of all kinds. And the thing that is, I think, most significant is it's kind of a sort of multi-paradigm approach to data science. You get to, you have data, it's got images. You have data, it's got text in it. And then you want to use machine learning and you want to use some fancy neural net technique or something. Well, those things will typically just be built into our language. So you can expect to go right from sort of, taking your images and identifying things in them and then clustering them and comparing them with something else. And this is all stuff that is integrated into the language. And with this notebook paradigm that we have, it's possible to kind of record what you did and then generate reports for other people that are interactive. We actually just recently released the capability for people to freely publish notebooks on the web. So you can take this notebook, you might have created it on a desktop system, or you could create it in the cloud as well. But you've done this big data science study, and now you just press publish, and then it shows up as an interactive document on the web. So anybody can then go in and explore that data and move some slider around or whatever else, or they can make their own copy of that notebook, could be still in the cloud, and redo a computation using, changing some piece of the computation that was specified by the computational language there. So I think this is a really powerful way to do data science, this kind of multi-paradigm approach, and the fact that you have this computational language which says this is what I was doing in this particular, making this particular plot. Here's the language. It's 1 or 2 lines. It's easy for a human to understand what that was. Mm-hmm. This is what I did. Here's the result. And from a sort of organizational point of view, it's something where you get to record that knowledge. And then when some other analyst comes in, next month or next year, they get to see what you did. So it's now, actually, let me talk about another big use of Wolfram language, and that's Wolfram Alpha.
Right.
So Wolfram Alpha is about 15 million lines of Wolfram language code, and it's a big production application that powers computational knowledge for a bunch of famous intelligent assistants and so on. Actually, the version of Wolfram Alpha that people usually see is the public version, the one that you see in
WolframAlpha.com, right?
Yeah, WolframAlpha.com. Widely used by professionals, even more widely used by students and so on. There we go. Boy, if we can put up things on computers, I could demo stuff. Wow.
What do you want them to type in? What do you want them to type in?
Oh, I don't know. A good party trick is type in a first name, and go type in your first name and
okay.
Okay. Oh, wow, you have an unusual first name.
I do. How about try it with a C? That's the one from the Bible. Let's see what happens when that pops up.
Okay, so now scroll down a bit.
Okay.
Okay, you'll have a plot of what the distribution of years when different people born with that name were born.
Oh,
Wow. Your name is becoming your modified name is becoming very popular. Look at that. The most common age for somebody with that name is 2 years.
Oh, wow. So they're
but a really good party trick is type in somebody's name, and it's just the way probabilities work. There's a pretty decent chance that the peak of the distribution, the most common age for that name, will be the actual age of the person who has that name that you're talking to.
Oh, wow.
But it's just, one of those things that's computable in the world that you might not think was computable in the world.
So something that I found fascinating here, Karsten, so that's a good, Karsten is one that's running this right now.
Karsten, okay, so it picked up as default was a glacier. So you go up at the top there, go up at the top to the blue thing at the top, and you'll see, assuming Karsten is a glacier, right underneath the input line, use the species specification. No, I don't think you want a species, or a given name. That's the winner there. Okay, let's see what happens with that. All right, a bit scratchy, but the most common age for that it says they're expected to be 2,153 people with that name in the U.S. population today, and the most common age for a Karsten is 4 years. So if you have a kid you just named Karsten, then
it's a very popular name for the
right. And then in the future, when the parents say, we come up with a really creative name for you, and you discover it was you were at the peak of the distribution that year, you kind of know what to make of it.
What I'm loving is I was able to type in Bulbasaur versus Charmander, and you have the complete Pokédex in here. To show the different types of Pokemon, their height, their weight, their even down to the proportion of females and males of the species, what they evolve from and into. So this is a curious thing for me, simply because I'm wondering, how often are you adding new information to the database, and how do you decide what goes in there? Because speaking pop culture wise, you could very well have left out these Pokemon if you wanted to, and look, there's even a way to show them as curves on computationally.
So data is flowing into Wolfram Alpha basically every second. There's whatever it is, whether it's flight tracking data, whether it's that's weird, whether it's whether it's data about box office data from movies, or whether it's lots of kinds of things. In terms of different domains that we add, one of the things that's great is there are billions of actual queries, so we know what people think they should ask a computer, and so we got a giant to-do list from that, and we're steadily working on it. It's going to take decades, and by the time we finished it, there'll be new things that have to be added.
Right.
But that's a great sort of source of prioritization, is what people think they might ask. Now, what's interesting is, as you look at different use cases for knowledge, different kinds of things get asked, even between what people ask phones versus what people ask, intelligent speakers or whatever, versus what people ask in cars. Those are all different. The real, like talking about Pokemons or something, if you were using that in Wolfram language, you would be able to, apply machine learning to these Pokemons and cluster the Pokemons and show, make a feature space plot. I might be able to guide you through if you're on a computer there. If you go to, let's see, the best place to go to wolfram.com.
Okay.
And let's see whether we can get you to just wolfram.com. Just wolfram.com, not Wolfram Alpha, wolfram.com.
Okay.
Let's see if we can. I have never tried doing this, a remote control guidance through, let's see.
This should be fun.
Scroll down a bit. I think you might go to let's go to scroll up. Go to, go to for students there. For students, there you go.
Okay.
Let's see if I can guide you to, okay. Scroll down a bit to free resources, Wolfram Programming Lab, and the Wolfram Open Cloud. Okay. Oh, that's bad. Oh, that's the wrong place to go. Okay, what you want to do is go, let's see. Okay, go to Wolfram Language. Go to on the right-hand side there. Go, I'm about to find out. Okay, and now scroll down a bit. And yeah, there we go. Start writing your own code in the cloud. Just right underneath where your cursor is. And let's see what that does. Just click it, I hope. Click it.
Oh,
what happened
we
there?
clicked it. It's not going anywhere.
What is happening?
Oh, I bet it's blocking a pop-up. Let's see if we can't.
Try.
You might try command clicking. I'm not sure if that will.
Yeah, we've got a
pop-up blocker.
pop-up blocker. So
Okay,
it's
then
not
go
letting
to
us do it.
go to Wolfram Cloud. Let's see. That's not going to work. I think you can go to. What you need to go to is the Open Cloud, and
Let's see.
I'm almost having. No. Well, you could try. I don't know whether that. Try. Try that. Might get you somewhere. No, that's not it. That's just a. Okay. What you need is the. That's all. Try Programming Lab there. Maybe that will get you to something where you can just. Actually, Cloud Basics, sign up for free access. You can go to the top there. That's one. There's some way you wouldn't have to sign up, but that one. Sorry, you got to sign in to something.
We can cut back to me while he's signing up. We'll come back to you.
Just and then we'll try and see whether we can do something with Pokemons by remote control. I have never tried this of telling somebody how to write code on a show like this by remote control.
Yeah, this is a first. There's a first for everything. But
Yes.
So speaking, I want to while we're getting all that signed up. You obviously, the front-facing version of the site at wolframalpha.com, it was one way that folks could go and you could get queries. And then the other ways through companies that were using it. How helpful was it for Wolfram Alpha and the Wolfram language and the Wolfram engine to become a part of the smart assistants that are out there, to become a part of Amazon's virtual assistant and Siri, in terms of learning what people wanted to learn? Was that a more positive thing for you, or did that end up being sort of, at least in the beginning, kind of an overwhelming thing to have to comb through?
No, it's actually not that overwhelming. It's kind of bizarre in some cases what people, the different kinds of things people ask and the different kinds of things they imagine computers will know. Mm-hmm. I mean, no, I think the thing that is more of a challenge is we just have a huge amount of knowledge about a lot of different kinds of things, and it's like, what could you imagine you could ask your computer? I mean, there's things that you could imagine you'd ask your computer, and I'm sorry, but our civilization just doesn't know the answer. Even some basic question, I don't know, how many wild foxes are there in America? We just don't know.
Right.
There's probably some estimate. Maybe we even have an estimate for that one. But it's the line between. But if you say, how many cows are there in America? We know that. The U.S. Department of Agriculture surveys those things. We know the answer. So it's a question of more of kind of what the boundaries of knowable knowledge are for people. I would say it's always interesting. I mean, in another use case, we talked a couple of times about computational contracts, but one of the places where those show up is you need a source of computational facts for a computational contract. Imagine you're writing some smart contract on some blockchain and it's, I don't know, weather insurance or something. Well, you need to know ultimately, did it in fact rain and wherever at such and such a time? And for that, you have to go to a source of computational facts. And we're kind of the only game in town for sort of a broad spectrum source of computable facts. And so we tend to be the place where people come for those kinds of things. And again, the types of facts that people want when they're using them in computational contracts on blockchains is, again, yet different from the kinds of things they want for an intelligent assistant that's based in their kitchen, for instance. In the kitchen, it might be, can a dog eat X? It's very different from, was there an earthquake in such and such a place or whatever? And I think it's I mean, we've been very much sort of in the tradition of we just make tools and sell software. We're not in the world of we're going to give you something, but we're going to keep all your data and so on in terms of users. Our model is very much of the we make stuff and we give away a lot of things. We sell things to people who can get value from what we're doing, and it's kind of what you do with it is your own business, so to speak. We're getting a certain amount of information from sort of anonymized queries and so on in the aggregate, but it's not our model or our interest to kind of sort of dig too much into the into the details of what people are doing with our products.
Right.
It's kind of we make tools, we hope people will find them useful, and that's kind of our model for operating in the world.
Update: we do have access now.
Yes.
So,
I'm in.
All right. Okay.
Wolfram
Just
Cloud.
type 2 plus 2. That's a good to just see. So this is in the. Okay, and then press Shift. Hold down Shift and press Enter. Shift Enter. Let's see what happens. Okay, very good. All right. Why don't you type like 1,000 and then exclamation mark 1,000 factorial? Let's just see if no, new line. Just click underneath 1,000 factorial. And then hit Shift Enter, see whether that's working. Okay, all right, all good. All right, so let us try doing something like well, we could do let's do let's say you type control equals, hold down control, press equals. Okay, now type US state capitals. Okay, now just hit enter. Okay, now what's going to happen is it's going to take that piece of natural language. All right, now press shift enter. It took that piece of natural language and it converted it to computational language.
Okay.
And now hopefully we'll be able to compute the answer. Okay, there we go.
Wow.
So now try typing geo list plot. So geo with a capital G, EO. Geo, okay, now list with a capital L. Oops, no space, back up. List with a capital L. Okay, now hit the autocomplete there. Okay, now type open bracket, a square bracket. And now type %. And now type close square bracket. And press shift enter. Let's see what happens there. And maybe what we can do, okay, there we go. All right, so there's a map. You can resize that. Just you can pull it out and resize it if you want. So there's just a map of the positions of the state capitals in the US. And so it's kind of, let's do something more exciting. Let's say, we'll do another geo type thing.
Okay.
Type geo nearest, geo, and then nearest with a capital N. Okay. Go ahead and hit the autocomplete open bracket. And then double quotes. And then volcano with a capital V.
Ooh.
Yeah, we'll see what happens here. And then comma. And then, I wonder where your web, okay, type here with a capital H.
Okay.
And then comma 10. And then close bracket. And
Shift enter.
shift enter.
Okay.
And see what happens. Okay. All right. Well, now, okay. So that was a list of the nearest earthquakes. So now we could pick. Let's take the first of those earthquakes. So say,
or is it volcanoes?
Oh, volcanoes. Sorry, for volcanoes. You can select it and you can copy it if you want to, but might be easier. Go ahead. No. Just type first. Type the following. Type geo elevation data. Okay, and hit autocomplete. Open bracket. Let's see. Boy, I have not tried doing this by dictating it to somebody. Let's see, geodisk. How about typing geodisk? And capital D. And D-I-S-K. Open bracket. Open bracket, not a brace, a bracket. And then first with a capital F. Open bracket. And then percent. Close the bracket. Then comma. And let's see how big a radius. Let's say 2 miles. So type control equals. And then 2 miles.
So that control equals is a way to use natural language and have it be turned into the computative the computational language.
Yeah, hit return there. I think it'll still understand what that is. Okay. And now close bracket and close another bracket. And now hit Shift Enter. And now hopefully. Okay, good. Now type list plot 3D with capital P, and then 3D, the second one there. Open bracket, percent, close bracket, and then hit Shift Enter. I'm living dangerously here. I don't know what's going to happen. But
Isn't that kind of the fun of this, though? Oh, my goodness.
Oh, there we go. Okay, now you can probably rotate that around on the screen. No, you can't. It must have been, I think there must be too much data. It doesn't want your web browser to crash. If you, but anyway, so that's the elevation data around that mountain.
Oh.
That's what we just asked it. So read the code. It says geo-elevation data of a geodisk that's 2 miles around the first thing. So we asked for the nearest volcano, 10 nearest volcanoes to here. And then we're asking for so you can kind of get a sense of what's going on here. In list plot 3D, we take the list of data and make a 3D plot. And that's the result we get.
Excellent. Now,
okay, should we try one more thing?
Can we do it with the Pokemon? Is there something that
we should be able to. Let's do, okay, why don't we do random entity.
Capital R?
Random, capital R, random entity. Close bracket, open bracket at the end. Quotes Pokemon. Okay, quotes Pokemon, close bracket. Close double quotes, comma 20. Okay, so now we should get 20, go ahead, close bracket. We should get 20 random Pokemons. Okay, now, why don't you do this? Say entity value. Open bracket, percent. Percent means the most recent thing that was generated, comma, quotes, image with a capital I. I don't know. I think there'll be one of these. Let's try it. Close bracket. Shift Enter. See what happens. Drum roll. Don't know what's happening.
Excellent.
Right. Now, okay, scroll down. Now type feature space plot.
I love this right now. This is awesome.
Okay, now just open bracket, a percent. Okay, let's see what this does. Close bracket. Shift Enter.
Here we go.
Let's see what this is doing. So this is going to use machine learning if all goes according to plan. I don't know if it will. It's going to use machine learning to try and figure out if we were to lay these things out based on their pictures in feature space. Oh, too big, 23 megabytes. Download for full functionality. Oh well. Okay, what you'll get there is a desktop notebook, but you'll have to download
the program,
the player. Let's see how we can do this. Okay, I've got a way to do this.
Okay.
We can recover. Let's just say thumbnail. No, it does new line. That you won't be able to. Okay, just say thumbnail. A capital T. and then, there we go. And then type /@, and then type %, and then whatever that output line number, actually % will work. Just double
%, okay.
Yep. That will give the 2 lines back. Okay, try that.
Shift Enter?
Yep.
Okay.
See what this does. What that is hopefully going to do is to make smaller images with less data from those Pokemons. Let's see if this works. It may have to send the data back and forth to the cloud. Hope that'll work. If that works, which it's a little disappointing that it isn't working so far, but if that works, then we should be able to do a feature space plot on those things. If that doesn't work, we'll do at least a second best here.
Okay.
Yeah, you can take, if you go up to those, I'll tell you what, go up to the Pokemons above and see whether you can select one of them.
Okay.
Will it let you select one? Yes. Okay, now type type copy. And now go down below. You copy that? Just no, not the image. No. Just go ahead and type Control C.
Okay.
Control C. Yeah, Control C. Yep. Just say copy. Now go down below, and just click anywhere. Now press paste. Command V. Control V. And let's see if that. Okay. All right. Now you've got that picture. Okay. Yeah, you can get those. Okay. Now. Okay, why don't you stop what it's doing there? If you go up to the evaluation menu, you can stop what it's doing. Go up to the evaluation menu up there and just say, no, actually, you just want to say abort evaluation above there. Okay. Let's just go ahead. Let's restart. Probably the easiest thing to do, it'll happen quicker, is just go up to evaluation and just say restart session. Okay. Up. Okay. Now scroll down. It reloaded. Actually, it's reloading everything.
I put everything back.
Okay. All right. So okay. Now go copy one of those Pokemons again.
Okay.
Whichever one you want. Command V, Command C, copy it. Now paste it down there. Just paste. Okay, now you're going to apply a function to that. So what you're going to do is click the cursor right before that guy. Click it on that line right before. Okay, now type something like edge detect with a capital E. And detect. Open bracket. Now, on the other side of that image, press close bracket.
Wow, so you can even use an image in...
Yeah, right. So, I mean, that's what you get for having a symbolic language, is that it doesn't care. It can be an image. It can be anything. So that just did edge detection on that image.
Wow.
So, and what we can, let's try one other thing just for fun.
Okay.
Instead of just copy, click down below, you can type Control L, and that should copy that line from above. I think that works, yes. Okay, now just go in and edit edge detect and change the word edge detect to, change edge detect to image identify. So this will use machine learning to try and figure out what this thing is based on, now hit Shift Enter. So it'll undoubtedly give a silly answer here, because we're showing it the thing which isn't part of kind of the natural world, so to speak, of things that it intrinsically knows about. Oh dear, that is bad. Okay,
14 minutes remaining. Oh, wait, no.
Oh no, there we go. We got it.
It guessed it was an orchid. That's a pretty good guess.
Well, let's see. Here's what you can do. You can go into that input line again and just click right before the close bracket. Right before the close bracket.
Okay.
Just right after that, right before the close bracket.
Okay.
And type all, all.
Okay.
Comma. Type a comma before the all. Comma before the all.
Okay.
Comma, all, comma, 10, comma, and then quotes probability. Quotes probability with a capital P. And then close quotes. and then Shift Enter, and let's see what it does. So what this should do is it should tell us, okay, so that's telling us.
It gives the probability that it.
Okay, imaginary being, it gave that a 3% probability. Okay, well, it was pretty sure it was an orchid.
Yes.
It was 47% sure it was an orchid. So that's the world of machine learning for you. You can't be sure of anything.
Honestly, the orchid is not a bad guess because that's what that Pokemon is based on. So,
right. But anyway, that gives some sense of what what this symbolic language of ours sort of looks like in the wild. There's a very, very tiny corner of what we do. Actually, if you want to see, if you go back there, you can pull up just the to give some sense of sort of the scope of what's going on. Mm-hmm. You can just pull up sort of the front page of the go there and go up in the documentation, up in the black toolbar, documentation. Let's see what you pull up there. So let's just give some sense.
Okay, yes, there are lots of different processes we
lots
can
of different kinds of things. So whether it's sounds or geometry or networks or whatever, that's always fun.
Can you make something generate a sound based on an input that maybe wouldn't normally like edge detect?
Let's take that Pokemon. Let's take that image of the Pokemon on line 1 there. Okay, I'm going to live super dangerously here. Let me see whether we can. What we want is an inverse spectrogram, and if you go back, just type inverse spectrogram. Spectrogram. Okay, now, unfortunately, I have to look at the documentation here. So hit the I button there. That's right underneath in that little raft underneath there, because I don't remember how to use this. There. Okay. So, I wonder whether we're going to be able to do that. What this is doing is it's taking, actually, you could probably record a sound. This is living very dangerously because it's going through the cloud. And as soon as you're dealing with audio data, it's large amounts of data that has to be schlepped back and forth.
Right. So you might not be able to.
You might not be able to do that. But what this would do is, well, you can try. Okay, well, we can. I don't know if this will work. Click underneath everything that you have there. Oops, what did you do? Something went weird there.
Escape.
Wow, your computer is set up in a sophisticated way. Okay, so hit underneath there. Actually, just go to the next line. Don't finish the inverse spectrogram for now. You could try typing audio capture. Actually, you know what? Try typing audio capture.
Okay.
Not sure if this is going to work yet, but okay. Hit it, and then type open bracket, close bracket. And let's see what happens there. And now Shift Enter. No, not currently supported in the cloud. Okay, can't yet do that in the cloud. I was going to say you could do an image capture, but then it'll take a picture of you based on.
Oh, gotcha.
So this one you'd be if you have the audio input to your computer connected to your web browser, et cetera, et cetera, et cetera. This all works a lot more easily just directly on the desktop. But then you could capture an audio signal and start processing it. Mm-hmm. We could.
And we don't have to show an example of this, but I'm curious. In theory, so earlier we made that 3D topographical representation of the volcano. Would there be a way, in theory, to take the sort of topographical thing and use that as waveforms to then output a sound? I don't know why anyone would need to do that, but that's so cool that you can.
Well, what's really easy to do, if you've got a bunch of notes, you can do it as a waveform. You can also do it as notes. So we could trivially, it's a one-line thing, to write something which will take some data and sort of sonify it, where we just say there's a thing. Well, you can take, if you want it as a waveform, there's a thing called list play, which will play the waveform, play a list of data as a waveform.
Wow.
Or you could do something else where you could make a bunch of notes played on a violin or something. You could have those be based on the values of the data. So these are, I've each of these things. It's kind of a it's really weird for me to I'm used to typing code with my own fingers, so to speak.
Right.
It's weird doing this thing of this is kind of high code art, so to speak. There's one thing doing live coding. There's another thing doing dictated live coding through the web. So this is a first.
I'm glad we could provide you with this new experience. Truly.
Yes, right.
That's been great. One of the things too that I want to note with Wolfram Alpha, even just online. So earlier you had mentioned something that people will often use or have asked their assistants is, "Can my dog eat blank?" And so while you were talking about that, I typed in, and I knew this fact: dogs cannot eat grapes, cats cannot eat grapes. But I typed in, "Can a dog eat grapes?" And what I like is that in any of these searches, these queries that you do, the first thing it shows you is input interpretation. And so you get an example of how the computer processes, or how the language is taking what you're saying and parsing it. And so you are almost trying to encourage the computational language literacy right there at the get-go, which is kind of nice. It's a little bit of it's practice there, because you see the thing is a dog. It's asking, is it safe to eat? And what is it that you're asking is safe to eat? It's grapes. And I like that.
Right. I mean, that's actually, we've been steadily going closer to, we have a new product that just came out called Wolfram Alpha Notebook Edition, which is kind of a merger of our Wolfram Language Notebook concept with Wolfram Alpha, where it explicitly shows you after sort of every input, you type your inputs in natural language, and then it shows you the conversion to precise symbolic Wolfram language, and then shows you the results. And it'll be interesting to see. I mean, that product initially is aimed primarily at the education market, and seems to, based on the first few weeks, it's doing exceptionally well. That's again, that's sort of helping to lead people into expressing themselves in computational language, which I think is it's just a really powerful form of communication for humans to humans, but also to their machines.
We'll have more with Mikah and Stephen Wolfram in just a second. What a great interview. But first, I want to interrupt briefly, because it's time to mention our fabulous sponsor, LastPass. This has been a great year for LastPass and TWiT together. We went to Boston in September for that great event. We've got more events coming up in 2020. And, of course, LastPass has bought the naming rights to the TWiT studios. So we just feel a real kinship with LastPass. And it goes back a lot earlier than their sponsorship. It goes back 10 years when I first started using LastPass. When I found LastPass, the ultimate password manager, I fell in love. About 5 years in, I told Steve Gibson about it. He interviewed Joe Segrist, the creator of LastPass. Joe was really generous, showed Steve all the software, explained exactly how it does it. And our security guy, Steve Gibson, gave it thumbs up. You know who else gives it a thumbs up? Our IT guy. Russell has given everybody in the building LastPass Enterprise. IT guys love it because, first of all, of course, you're securing every entry point into your business. Your employees have access to your databases, your checking accounts, your website, everything, right? You don't want them writing the password to your bank accounts on a Post-it note and sticking it to the monitor in the office. That's just not okay. But that's what they're going to do. That's why you need a great password manager like LastPass. It's really gone well beyond just being a password manager. In the enterprise, LastPass has added some really cool new features. Multi-factor authentication that uses more than just two-factor. It uses things like geolocation and IP address to make sure that the right people are logging into the right accounts. And as the IT department, you get a complete dashboard with all the visual input so you could see exactly who's using which assets, when and where. And by the way, employees don't even have to get the passwords. They just get to log in. And so that way they can never give away the passwords either. You're really protecting yourself. LastPass, the new enterprise version of LastPass, LastPass Business, has some other great features I'm really a fan of. For instance, single sign-on. This is something that kind of breaks my model of security. Normally, I think of security as being a trade-off between convenience and security. You know, more security, less convenient. No, that's why I love LastPass. It makes you more secure, but it's easier for your employees. Single sign-on is a perfect example. They don't even need a password. They use their smartphone to log into an account. Again, you get great granularity, great insight into who's using what where. They get quick and easy access, and it's completely secure. It's just one of many ways LastPass is getting better and better and better. So you've got password management, you get authentication solutions, you get access solutions. You can instantly add and remove team members. When we get new employees, we put them in the system immediately. And by the way, I'm such a believer in LastPass. We give every employee a personal version of LastPass too, because I want them to use it at home as well as at the office. That's actually a great benefit. I think our employees really appreciate it. You can store digital records. We put everything business-wise in there, our EIN, our Wi-Fi logins, our software licenses, employee IDs. At home, I store my passport in there, my driver's license, because it's an encrypted vault, only decrypted on device. No one can see this except me, and I use two-factor to make sure that's absolutely the case. And it's everywhere. You put the first thing I install when I get a new phone, a new tablet, a new computer, I put LastPass on it. That way I can get into all my stuff quickly, easily, and be more secure. Windows, Mac, Linux, iOS, Android, everywhere you are, all the browsers, that's where LastPass is. Russell, our IT guy, loves it because he can set security controls and restrictions, keeping the information, the critical information, local to just the need-to-know basis, right? I can go on and on. I want you to try it. This expanded business lineup has incredible features that both improve security and make life easier for your employees and you too, as it turns out. LastPass.com/twit. Find out how they can help you. LastPass.com/twit. We thank them so much for supporting Triangulation. And I'm glad that we got this great guest on. I'm so glad Mikah did this interview. More with Stephen Wolfram.
Well, of course, we brought you on the show for your new book that's out, Adventures of a Computational Explorer. Of course, in the book, it's essentially a collection of different pieces, correct, essays that you've written over time. But what I like is that, as is the way of things, there's sort of a flow between these pieces. It all kind of connects together. And I think it's a great look inside your mind, to be honest, and a great look at sort of your history of thinking, and just a fun little taste of some of the different roles that you've played, and working with Hollywood and things like that. So this is a fascinating read, and of course is available where all good books are sold. Right? It is out now. Yes.
Oh yeah.
Yeah. Adventures of a Computational.
It was. These pieces are always fun to write. So hopefully people find them fun to read as well. They were fun to write, and it's kind of it's interesting. I've kind of had this idea of using computation for everything, and that book is kind of a collection of tales of some maybe not so expected places that kind of the idea of computation has turned out to be valuable. And it's been I would say some are more outlandish than others, but as I say, they were fun to write.
Yeah, what's the technical name of spiky? That was one of my favorite reads.
The rhombic hexacontahedron, right? That's our actually, I like to study both, I like to sort of create the future of technology and science and so on, but I also am interested in history. And so, we have this three-dimensional object that is sort of the logo for our company and our products and so on. And I was like, where did this, what is the story behind this thing? And ended up actually with a bit of a historical mystery there there's a spiky. You can actually probably go, if you go to my blog post about the story of spiky, that's the history going back 30 years of our different spiky uses that you just saw. But it's something where it's kind of the history of polyhedra is quite fascinating. And there we go. That's me with lots of spikies.
Lots of spikies.
Lots of spikies. Spikies everywhere. It's just there's just a big long history, but it ends up in the most bizarre place. It ends up that in that particular case, there are fabric rhombic hexacontahedra that are common folk art objects in Brazil, and I tried to find their origin. And although I've done lots of history and I've been quite successful at kind of drilling down what really was the origin of something, that one I didn't ever figure out where it came from. It was an oral tradition that kind of dated from the early was sort of very active in the early 1900s. And the problem with oral traditions is nobody wrote them down.
Right.
But it's just an example. I think there's a lot of other funky things in that book about the digits of pi and extraterrestrial communication, and things about my sort of personal analytics of my life. I have, for better or worse, because I've been interested in data and so on. I've collected lots of data on myself. I think it's sort of an embarrassing and nerdy thing to say, but I think I've collected more data on myself than any other human has, because I've been doing it for a bit more than 30 years, and I've get every keystroke I type, and every everything, every email I've sent and received. It's about 3 million of them so far, and so on. And it's kind of interesting to see what one learns about oneself from sort of the data exhaust that one generates.
I love that, the data exhaust. I love that. And luckily you are capturing your data exhaust. I guess, where are you capturing that? In your own personal atmosphere?
Cloud. Yeah, right, something like that. Yeah, I mean, the real question for me is, we've done a lot of work on AI and so on, and it's like, from 3 million emails, could you make a bot of me that would where you could just learn from all those email responses and so on over the 30-year period? Could you basically, is there enough information there to reproduce sort of most of me and how I would respond to things? So that's sort of a fun thing that I wonder about. And it's I've been quite involved in a lot of questions about AI and about what's possible with AI, and kind of how to think about that. A few of those things are captured in that book as well.
Now that I think about it, you are coming to us from a very white room, and it could be that right now I'm talking to a simulation of you and not actually you. I don't know if there's any way that I can confirm that, but
well, that's a good question. Yes, right. It's always the Turing test, right?
Yeah. I need to get a Turing expert in here to test this.
Right. Well, the people connect Wolfram Alpha to Turing test bots, and the thing that's always fun there is it's kind of a guaranteed lose if you connect Wolfram Alpha, because all you have to do is start asking the bot all kinds of weird questions about different kinds of things, and if it can answer, it's not human.
There you go.
So that's kind of the
so yeah. How many wild foxes are there in the United States, Stephen?
Right. I don't know the answer to that.
All right, he's human.
I think the answer may not be known.
Oh well, see, okay, well maybe you are.
Some evidence there.
Well, I want to thank you so much for being here today and for giving us a disconnected guiding process through the cloud version of Wolfram Alpha. That was a lot of fun. I enjoyed that. I'm going to go home and play with all of that kind of stuff and see what kind of audio waves I can generate from it. So if you get any emails from me asking for support, you can just ignore those. I'll be fine. I'll figure it out. But no, we do appreciate you coming and joining us today, truly.
Great. Thanks.
Thank you. Of course, you should check out Stephen Wolfram's book, Adventures of a Computational Explorer. It's got lots of great essays in here about Spiky and about the history there. So it's a fascinating read. And what I like is that it's bits and pieces, but as you say, they sort of all fit together, which is nice. We record the show live every Friday at 2:30 p.m. Eastern. That's 11:30 a.m. Pacific, which is 19:30 UTC. So you can tune in live and join us in the chat room and hang out while we talk to the smartest people in the world about the most important topics in technology. Thanks so much for joining us today, and one last goodbye to Stephen Wolfram. Thank you.
Thanks. Bye.
Bye.